Okay, so this is the Cory-Seebach reaction. So, Cory-Seebach reaction uses 1,3-dithiones, this little reaction shown in the middle here. And when we react it with an aldehyde, we get this fun little sulfur protected group that we can then use to do a lot of things because we can form that sulfur protected group. And then using this mercury along with water and THF, we can then get ourselves back to that original aldehyde, which can, of course, be very useful. Um, in this instance, an aldehyde, this can just get you back to carbonyls in general. So then you can imagine that we can use this to attach carbonyls to our desired products. So this protecting group on its own is kind of lame. It doesn't do a whole lot just by itself. However, when we react this protecting group with butyl lithium, we can make it into a reactive species. So what we can imagine winds up happening, um, what this curved arrow mechanism is really meant to show that the electrons from the hydrogen go onto that carbon and it is stabilized by the lithium. So what you can really imagine is just this kind of nucleophilic carbon here, with of course the lithium stabilizing it. But this nucleophilic carbon can, of course, do a whole lot of fun chemistry as shown here. And we'll, of course, go into all that, but a lot of fun stuff going on. And we will start off with alkylation. So if we just have that protecting group with our lithium attached, it's now reactive. And we just introduce that to a carbon chain with a halogen attached. Then we can then put that, we can then attach it to that carbon chain in place of that halogen. And that's shown in this curved arrow mechanism here, where the electrons that are being stabilized by that lithium hop onto the carbon attached to the halogen. Those electrons kick onto the halogen. And then we kind of have our fun protecting group attached onto another carbon chain. And then we can just introduce our mercury attached to the oxygen and our THF again. And then we are just left with a nice ketone in its place. So definitely a very powerful reaction.
Another group that this reaction can be used with is epoxides. The mechanism proceeds as shown. The oxygen from the epoxide will be protonated. Then the reactive sulfur species will attack the epoxide, breaking one of the bonds between the carbon and oxygen. To expel the sulfur protecting group, mercury chloride and water is used. The sulfur will attack the mercury, expelling one of the chlorines. The second sulfur will use its lone pair of electrons to make a double bond, thus breaking the bond between the carbon and the sulfur with the mercury attached. A water molecule will attack at the double bond, breaking it and giving the sulfur back its electrons. A separate water molecule will remove one of the hydrogens from the OH2+. The oxygen from the alcohol group will then use its lone pair of electrons to make a double bond, expelling the sulfur group. Then another water molecule removes the remaining hydrogen from the oxygen. This reaction can also be used with the ketone functional group, proceeding with the mechanism as shown. Once the reactive species is formed in solution, it will attack the ketone at the carbonyl carbon, breaking the double bond and giving the oxygen back its electrons. The now negatively charged oxygen will grab a hydrogen off a hydronium, forming an alcohol. To expel the sulfur protecting group, mercury chloride and water is used. The sulfur will attack the mercury, expelling one of the chlorines. The second sulfur will use its lone pair of electrons to make a double bond, thus breaking the bond between the carbon and the sulfur with the mercury attached. A water molecule will attack at the double bond, breaking it and giving the sulfur back its electrons. A separate water molecule will remove one of the hydrogens from the OH2+. The oxygen from the alcohol group will then use its lone pair of electrons to make a double bond, expelling the sulfur group. Then another water molecule removes the remaining hydrogen from the oxygen.
The next reaction we have is that of the sulfur protecting group and acyl chlorides, which can be used to avoid those pesky methyl groups. The reaction is simple really. All that happens is that the nucleophilic lithium bond will attack at the carbonyl carbon and kick off the chloride, substituting the lithium with this ketone group. Finally, we can add nitrogens with the iminium ion. It may look really scary, but it's really quite simple at first. Since the nitrogen is positively charged, it's going to want to act as an electron withdrawing group, so the lithium bond will attack at the double bond carbon and kick up the electrons to the nitrogen. In the end, we'll end up with a substituted nitrogen group.
Now that you learned the Cory-Seebach reaction, apply your knowledge. We'll give you a synthesis problem. Try to get to the molecule at the bottom, starting with the molecule on top, using molecules with 5 carbons or less. Now we'll go over the solution in a bit, so make sure you pause the video. And actually pause the video. Now that you've unpaused the video, create the protective group. This is the first step in our synthesis. We want to react an aldehyde with a 1,3-propane dithiol in acidic conditions to create the 1,3-dithiane. Then, we'll react that with butyl lithium for the reactive species. In the next step, to add our first nitrogen group, we'll react that with the iminium ion. Next, we'll deprotect the carbonyl using a reagent we learned previously. Then, we'll synthesize the final product using reductive amination. And now, all the steps on one page if you happen to miss anything. Make sure to pay attention.